So as I was saying here, for the two design philosophies, we have the ASD and LRFD. It's okay to use either one of these two methods. And in each one of these two methods, you need to have a capacity to be greater or equal to the demand. Demand means the assigned loads that you want the structure to support. Capacity is going to be how much it's going to be able to support. For the ASD, when it comes to the demand, it's going to be the loads as they occur. There is no multiplier to these loads. For example, you're going to have the service loads. This is what we call here the loads as they happen. Dead load is going to be the self-weight of the structure itself and self-weight of items. Live load is going to be the occupancy load that you put to the structure. So what happened in this case, you're going to say demand is going to be service load, is going to be the self-weight of the structure besides, or on the top of that, you add the live load, which means occupancy load. I'm sure that there's other loads like environmental loads like wind loads and seismic loads, but just to get to the point, I'm not adding all the loads here. I'm just taking this couple of loads to use them as an example. When you do an ASD design, what you need to do is to add the dead load to the live load. And with that, you have the demand on a member. So let's say if it comes to a beam, if you have a structured steel beam that you'd like to design. So what you need to have is give you the moment and the shear. When it comes to the moment, as an example, you're going to have the moment due to dead load and moment due to live load. You just add them to each other. When it comes to the capacity here, you're going to have something that we call nominal strength. Nominal strength, and then you take it, you divide it here by a safety factor. Because you cannot just design for the nominal strength to be the same as the total load applied to it, which means once you approach, if I'm going to be doing this and not use a safety factor, it means once I approach here, the design load, which means I add the dead load to the live load, the structure is going to be reaching its failure point. So this nominal capacity is almost the same as a failure point. So you don't want your design load to be approaching or to be close to the failure point. This is going to be bad because it means once I approach here, total design load, building is going to be collapsing. You don't want, or it's going to be cracking, or it's going to be yielding a lot. You don't want this to happen. So usually you need to take this nominal strength divided by a safety factor. This safety factor, let's say it ranges from 2 to 3, roughly. And with that, you're going to have some safety margin, as we call it. So in the case of a beam, you have the beam yielding. And the nominal capacity, you see, this is going to be M sub n. M is going to be the moment, N is going to be the nominal capacity, stands for nominal capacity. Is going to be equal to the yield strength divided by Zx. Zx is, you're going to hear definition for it, or just Z, the plastic section modulus. I'm sure that you guys went through this already. You know what this means by Zx. Now the allowable moment is going to be equal to the nominal capacity. Divide this by omega sub 0, which is the safety factor. It's right there. Just M, if you say M in ASD, it means the demand, the applied load. And M allowable is going to be the allowable load. So in this case, I need the allowable load or allowable moment to be greater or equal to the moment demand. And with that, I'm going to go here back one step to the previous slide and just come back here to this equation, which says here capacity is going to be more than or equal to the demand. So I was able to provide this in this equation here.
Sir, doesn't M stand for bending moment?
Yes, M is going to be the bending moment. This is correct. And M here is going to be the moment demand, which means the addition of the dead load and live load, if you like, consider these two loads. So this is going to be the load that you want to support, or the moment that you want to support. And this moment here is going to be the moment that your beam or the beam section that you picked is going to be able to resist. So you want to be sure that the resistance or the capacity moment is going to be greater than the moment demand that you want the beam to support, if this makes sense. Are you good?
Yes, thank you.
All right, no problem. Now, how about LRFD? What happens here in LRFD? So in LRFD, the loads is not going to be just the loads as they happen. It's not going to be the service loads. They're going to be factored loads. And in this case, it's going to be called M sub U, which means ultimate load, ultimate moment. This is going to be, let's say, this is going to be for axle load. P is going to be used for axle load. T is going to be used for torsion. So it's going to be T sub U, P sub U, which means the ultimate axle load, ultimate moment, ultimate torsion, if you like. When you have a beam, you really care about most likely the moment, number one. And of course, the shear is going to be there. But just as an example, I'm just taking here M sub U. So M sub U here is going to be equal to the loads or to the moment due to dead load and live load, and then you multiply them by some factors. This factor is going to be more than one. Like if you guys remember, when it comes to dead load and live load, we say 1.2 dead plus 1.6 live. So this 1.2 and the 1.6, this is what we call here load factors. So this here, when it comes to the demand, when it comes to the capacity here, we take the same nominal strength that we have used in ASD. We're gonna go back here one step to ASD, same nominal strength, this one here. But instead of dividing it by a safety factor, we're gonna multiply it by a strength reduction factor. Let me go back one step to the ASD. This safety factor is more than one. So for example, if I'm going to be using safety factor of 2, I'm going to be taking this allowable moment to be equal to the nominal moment divided by 2. In the LRFD, I'm going to be taking the nominal moment multiplied by a factor which is going to be less than 1. In our case here is going to be 0.9. So the moment capacity is going to be lower than the nominal capacity. At the end, the moment capacity is going to be greater or equal to the moment demand. So in both of these two methods, we're going to go back here to ASD. You have here the allowable moment is more than the demand moment. In the LRFD, the capacity moment Vman is going to be more than or equal to M sub U, which means the demand moment. So what is the difference between the two? Let me compare here demand to demand. What happened here in both demands? The demand in ASD is going to be just the addition of dead load plus live load. The demand when it comes to LRFD is going to be magnified demand. Why? Because I'm going to have this load factors 1.2, 1.4, 1.6. So I'm going to have some load factors. So this demand is going to be higher than the actual loads. While in the ASD, the demand is going to be like the actual loads. Now I understand the difference between the two. In ASD, I'm going to have the loads as they happen. In LRFD, I'm going to have the loads multiplied by some factors. Now let's look here at the capacity. The capacity in ASD is going to be equal to some nominal moment or capacity divided by some safety factor, more than 1. Let's say it's going to be 1/2 of the allowable moment. So all the safety here, I'm going to put in the capacity while there is no safety in the demand. So the safety margin here, I'm going to put it here by taking the capacity divided by a factor, more than 1. When you come here, look at the capacity, you take here the nominal capacity, you multiply by 0.9. So it's going to be 19% of Mn, while in the ASD, it's going to be, let's say, 50% of Mn, which means, now to summarize the difference between ASD and LRFD. In ASD, all the safety is going to be right here. All the safety in the entire design is going to be only in the capacity part or side. In LRFD, the safety, one section of it is going to be in the ultimate load, in the demand. The other section of it is going to be in the capacity side, which means the loads, you're going to have here a safety with it because you need to multiply by a factor to increase it. And also the capacity, you're going to have a smaller factor. Smaller means it's going to be 0.9, it's going to be less than 1, then 1 to be used to bring it to the capacity point. Any questions on this? Yes?
Professor, it's usually said that ASD is very conservative, but as you explained, LRFD looks more conservative because we apply the load factors and we also apply the fee. So can you explain a little bit more which is more conservative? And yeah.
Yeah, I'm coming to that. But I just want to be sure that I'm clear on where the factor is going to happen here, or where the safety is going to happen here, where we take it here and where we take it there. So the question is, if I'm doing here a design, which method should I use? Should I use ASD or should I use LRFD? This is going to be the question, right? So I'm going to say most likely you're going to be using LRFD these days when it comes to structure steel. ASD is more conservative. It's going to give you larger sections, larger steel sections. But when you look at the ASD, it's going to get you larger sections. Don't forget, ASD is going to be like the old method, and LRFD is like the new method. Let me tell you the reason. In ASD, let's say the load is equal to 100. Let's say, I'm just making things up here, making numbers, just to make it more understandable. You have a moment demand of 100 units. When it comes to capacity, let's say Mn is equal to 200, exactly 200. Safety factor, let's take a safety factor of 2, which means now your capacity is going to be equal to 100. Why? Because you take the 200 divided by 2 is going to be equal to 100. Now they are almost equal to each other, which means good because I was able to satisfy this equation. All right. Let's take the same two numbers, which means 100 for the demand, the service level, and 200 for Mn, and let's see what's going to happen if I'd like to use here LRFD. Now, number one, this 100 is going to be multiplied by a factor, and this factor, let's say it's going to be an average of 1.4. All right. So the demand now becomes 140. Why? I have 100 as a demand, service demand that I have taken from there, multiplied by 1.4. The load factor now I have about 140. Let's look here what happened to the capacity. I'm going to be taking here 200, and the fee factor is going to be equal to 0.9. 0.9 times 200 is going to be 180. Now, if you like here to compare, if I like to compare, I can do this with you. You guys see my screen, right? So what I'm saying is, if I'd like to do here ASD, so I'm going to write here ASD. Let me make it a different color. If I have here ASD design, right? So I'm going to say here ASD design. My demand, so I'm going to say here demand, is going to be equal to 100. So I'm going to say here demand. Right? The capacity, I'm going to say capacity, is going to be equal to 200 nominal. Divide by 2 is going to be equal to 100. Yes, how about a lot of D? Here's a lot of D. In the demand, I'm going to be taking the 100 times 1.4. With that, I have here 140. The capacity is going to be equal to 0.9. The fee factor, multiply this by 200, is going to be 180. Now let's do the comparison. In the ASD here, the demand is exactly the same as the capacity. This with a specific design or choice that we have picked certain beam. For the same beam here, look at this. Capacity is going to be equal to 180 and demand is going to be equal to 140, which means we have lots of margin here. which means if I'm designing here with LR of D, I could have pegged a smaller beam section and make it work. Does it make sense now? Yes?
Yes, thank you.
All right, very good. So let's go back here to our business. All right, now load factors. Now I'd like to talk here about load factors. For load factors, as you see here, this is going to be based on the code. Now, which code? This is going to be based on the CBC and IBC. It's going to be based on the EGCE 7-16. You have all of these load factors. When it says here mean D means dead load, here's definition. It says F is going to be fluid pressure, like if you are doing a water tank or whatever, right? And then you have L, which means life load. So if you don't have F, don't use it. If there's no water structure here, water tank, don't use this. There's no load. Same thing, forget about H and F. So let's just skip all of these loads and say that all what I have here is going to be dead load and life load. How about the rest of the loads? I don't have them. So if I'm doing here ASD, I'm going to be adding dead load plus life load. So this here, when it comes to dead load and life load and load factors in ASD, I don't have any, just equals to 1. If you do LR of D, they say the following. Take 1.4 times dead load. If this is going to be dead load, this is going to be the only loads that you have. Compare it with 1.2 dead plus 1.6 live. Someone's going to say, how about F and H? And let's say we don't have it. So our structure do not support any of these loads. All what I have is dead load and life load. Code says, try 1.4 times dead, compare it with 1.2 dead plus 1.6 times live, take the larger of these two. This is what the code says. As you see here in the LR of D, I have some load factors, and this load factor is more than 1. If I go back here to ASD, load factor is going to be equal to 1, which means the demand is going to be equal to the service load. There is no change. Are you good? Any questions on the load factors? Yes?
Nope, all good.
You're good. All right. Now let's talk here about the structural steel properties as they happen. What I really care about when it comes to steel design is going to be a few values that I need to consider. This is here, as you see, this is going to be the stress-strain relationship for structural steel. You bring a spacer with steel, you apply tension to it. So this is going to be like the tension test. At the beginning, you're going to have this elastic performance. You add some stress, you have a strain till you hit here the yield point. So we call this region here is going to be the elastic performance of the steel displacement. Once you reach to the yield point, you're going to be at the yield stress. So F sub Y is going to be the yield stress. What is the yield stress? It's going to be the stress at which the steel is going to start to yield. At the same point, I'm going to have a point here in the strain. I'm going to call it epsilon sub Y, which is the steel yield strain. The slope of this line here is going to be equal to the Y component divided by the X component. We call it modulus elasticity. It's going to be E sub S. So what is E sub S? It's going to be equal to F sub Y divided by epsilon sub Y. For almost all the steels, this value is constant, is equal to 29,000 KSI. Now units for the stress is going to be KSI. Units for the strain is going to be unitless. Strain doesn't have any units. This why this slope of this line is going to be also in KSI. When you take a stress unit divided by no units or unitless, it's going to be the same as a stress unit. Once the steel here is going to be hitting the yield point, it's going to show no resistance at all for some time. At one point here, it's going to start to pick up again. So the stress, some resistance is going to happen in the steel displacement. We call this point here the strain hardening point. And with that, you're going to gain here some resistance till you hit the ultimate, which means maximum stress that the steel can see is going to be F sub U. After that, you're going to see here the stress curve here is going to decline, and at certain points it's going to fail. So it's going to be the failure point. This point here, we call the maximum steel strain. SM is going to be the maximum steel strain. It doesn't happen with the maximum steel stress. So a few values here that I need to consider is going to be important to me. The first value is going to be simple. It's going to be E sub S, which I'm going to be considered to be 29,000 KSI for all the steels. As long here I'm going to be doing a design, it's going to be 29,000 KSI. The second value I need to be concerned about is going to be F sub Y, yield strength. The third value is going to be F sub U, ultimate strength. So it's going to be like the three values I need to be concerned about. About absolute SM, not very critical. Absolute sub Y, you can figure it out because you have ES, you have F sub Y, you can figure this out. How is that? You say ES is going to be equal to F sub Y divided by absolute sub Y. If you have ES 29,000 and you have FY, let's say 50 KSI, you should be able to figure out absolute sub Y, but we don't need it in the simple design. It's not critical. The structured steel shapes. When you buy structured steel, you're going to have something like an I-beam, we call now W-shaped section. We have the C section, which is a channel section. We have steel angles. We have a standard steel pipe, like regular steel pipes that you see, round sections. And also we have this HSS properties or HSS. This is hollow steel sections, if you like. So we'd like here to go through the steel manual and see what information we have about this when it comes to section properties. Section properties is giving the first section that you have here in the book. I'm opening it here for you. You have a copy of it. So we're going to have here section properties. If you look in the tabs, as I say here, part 1, and you can read it yourself. You have about sections and properties. Here's a scanned copy of the code itself, or the steel sections. Actually, this is not the code. As I say, this give you like the design aids. This give you the table for the W shapes. They give you a picture of the section that you're going to be providing here for you. Here's the X axis, Y axis, the total depth, which means from the top all the way to the bottom, we call this D. We have this going to be the width of the flange, is going to be B sub F, F stands for flange, and usually B is used for the width. We have here TF, which is the flange thickness. We have the web thickness, it's going to be TW, the web thickness. We have some other variables like T. See this curved area here, from here to there, this gives you like the flat area of the web. And then we have K, which is this region here, that we are gonna have this round shape in there. Let's see the information available here for us. The shape here, one of the shapes or one of the sections you may call W44 by, let's say, 290. What is that? The first designation here is gonna be the depth. And the second number here is going to be the weight, as in pound per linear foot of the beam. So the total depth of the beam is 44 inches. And the weight is going to be 335 pound per linear foot. Same thing here, by 290 pound per linear foot. So the depth of this is very same like this depth. Look here at the depth. 44 inches, 43.6, 43.3, 42.9, which means this is like the nominal depth. They are very close from the 44 inches. So this beam size here is going to be called W44 by 262. Nominal depth, which means it's very close to be 44 inches, but we call it here 44 by 262, and the actual depth is going to be 43.3. Here's the cross-section area given to you. So you don't need to make it up. You don't need to calculate it out. It's just provided here to you. You can just use this here in your design and analysis. This depth here, as you see, I have a number with decimal and I have a number with a fraction. This number with decimal point, this is what you can use in design. This one here, what you can use for construction. In construction, you're not going to be talking to an iron person, an iron man, and then tell him, hey, it's going to be 43.6. But you're going to be using fraction of 8 inches and 16 inches. In this case, you're going to call it 43 and 5/8. If I'd like here to show a number in a design drawing, this is going to be the number I need to show. If you like to see shop drawings, it's going to be all written in these numbers, not these numbers. This number is going to be good for analysis. This number is going to be good for construction and for drawings. Web thickness, look at this, 1.03. For construction purpose, it's going to be called 1 inch. You cannot call it 1.03. You cannot measure the 1.03, the 0.03. It doesn't make any sense. It doesn't make a difference because it's going to be within the tolerance. Same thing here. Look at this number. This is not 7/8. This is not 13/16, but this is the actual values. So if you like to do analysis, you use these values. You don't use these values. Same thing here for the width. Look at these values compared to these values. In our analysis, we're going to be using this, not this. Same thing for the thickness of the flange. This is going to be the flange thickness. Look at the numbers here, 177, 1 3/4, which means 7.5. Which one to use in the analysis is going to be this one. Here's K, this for detailing and this for design. In here, they make a difference. They want you to understand the difference between K design and K detailing. And actually, this is going to be TF detailing. This is going to be TF for design. Same thing here with for detailing, for design. If you like to draw a detail, this is going to be the number that you use. If you like to do analysis, this is going to be the number you use. This is going to be in your design. What is K? K is going to be this distance here. All right, let's see here the S shapes. This is going to be the standard shapes, standard I-beam shape. Total depth, width. So what's the difference here? This is going to be wide, which means the flange is really wide. This the flange is going to be kind of narrower. And you're going to have the sections going to be called S. Let's say 24 by 106 or S20 by 86. And then you can see here all the information about it. So I have here the W section and then the standard section. After that, we have the miscellaneous section. M shapes means miscellaneous shapes. So M, you have M, let's say 12 by 10. What is this? This is going to be a beam. It has a depth of 12 inches and the weight is going to be 10. And then you're going to see here all the numbers for it, all the values for it. HP shapes is generally speaking, they are used for piles. So they look like an H and used as piles. And here's the designation of the section and also all the variables. Here's the C shapes. It's going to be for channels. Same thing. You're going to have same symbols. TF, depth, web thickness, and the whole thing. So you have here all the information. And this is going to be C, let's say C 12 by 25. And here's all the properties for this choice or for this section. MC means miscellaneous channels. The very famous one is going to be 12 by 10.6. It's going to be very common because it's used for stereo stringers. So any stereo stringer most likely is going to be made out of MC 12 by 10.6. Unless it's really very heavy, you're going to be going to 12 by 20.7 or 12 by 25. But most likely it's going to be this section here. This one included in this table. Then if you're looking for any of these parameters, you're going to have a picture here that shows you exactly what you're looking for. Any questions so far? Yes? Hello?
No, all good.
All right. So have you
Sir, what is the difference between MC and M section? MC and C shape.
Yeah,
sorry.
the MCs and Cs, usually the MCs get be lighter, which means for the same depth, look at this. You have MC, it goes all the way to 10.6. Look at this C, it goes only to 20. So this like heavier section. The flange, thickness, and this is going to be like heavier. If you like to go a little bit cheaper, you're going to be going with this. So as I was saying here, MC 12 by 10.6, look at this. You have the weight of 10.6 pound per linear foot and the depth is 12 inches. If you like to gain the same depth, look at what happened here to the beams or to the channels. I'm sorry, to the C. It's going to be at least 20.7, which means the weight is going to be double.
Okay, thanks.
All right, are we good? Okay.
What was the difference between K design and K detail? Can you go over that again, please?
Say it again. Difference
The
between
K design and K detail, I believe, and the other.
oh, this one,
section?
detail and design. Okay, generally speaking, when you look here for all of this information, it says width, thickness, depth. You're gonna see here two numbers, right? One number is gonna be for what? For the actual depth for design, and this gonna be for detailing.
Oh, okay.
Look at this. Thickness, 0.52 or half inch. Which one should I use if I'm doing a design like calculation analysis? Gonna be this one.
Okay.
This one I'm gonna be using if I'd like to develop a detail.
Okay.
Okay, good. I guess with that, we're going to be stopping at this point. Please, in your way out, in the chat section, I want you please to type your name before you go. And I'll see you Thursday, same time. Excuse me, Wednesday, same time. Any questions before you guys go?
None here. Thank you.
Thank you, Professor.
Thank you, Professor.
Thank you,
Professor.
Wednesday.
Thank
You have a good
Thank
one.
you, Professor.
All right.
See you on Wednesday.
All right, thank you.
Sir, I have a
You guys
question.
have seen the homework. It should be very simple. It's just a structure analysis that I want you to solve. Just to refresh your memory and just be ready to do some structure analysis with us.
Professor, I have a question.
If you have any questions, I'm going to be available tomorrow at the office hour. You can come back and ask any questions about the homework if you want to.
I have the 2005 edition of the manual of steel construction. Does it suffice, or I need to?
Yeah, it should be fine. It should be fine. And when you do your analysis in the homework or exam, please be sure that you indicate which version they've used, because there's some differences between the two.
Okay.
Sir, about the assignment, do we just have to make the shape of SFD and VMD, or do we have to also mention the values that they are getting?
You're talking about to mention in your analysis, to mention which version to use, right?
No, sir, I'm talking about the assignment. In the assignment, do we have to mention the final result values, or do we just have to draw the shape?
Yeah, when you do a design, you need to finalize your analysis, right? When you do any analysis, you need to give me the final numbers, right? If I understand you correctly.
Okay.
Did I answer your question, or?
Yes, it did.
Okay, right, good.
Can we type the assignment, sir?
What's that?
Can we type the assignment, or just we need to put it on a piece of paper?
You can type it, you can print, you can do handwriting, but please be sure it's clean, and then you can scan it and upload it.
Okay, thank you, sir.
No problem. Right, you guys have a good night.